In this video, I'm going to describe to you how the layers of an OPC UA communication stack are implemented using actual technologies that are in existence today. These layers are data encoding, data security, and data transportation. My name is Kudzai Manditereza with Industry40.tv, and I regularly publish industrial Internet of Things videos on this channel. So if you're new here, please do subscribe to make sure that you never miss any of the videos. A quick thank you to our sponsors. This video is made possible by our friends at HiveMQ, who are providers of an enterprise-grade edge and cloud-based MQTT broker, and Opto22, the manufacturers of reliable industrial controllers for automation and IoT applications. Okay, so in the previous video, which focused on OPC UA services, I described to you how messages are exchanged between an OPC UA client and server. Now, what we did not discuss in that video is specifically what technology is used by OPC UA to A. Encode those messages, B. Apply security to the messages, and C. Transport them from client to server. And that is because OPC UA services are nothing but abstract definitions. By choosing not to attach its services to a specific set of communication technologies, OPC UA leaves room for integration of any future communication and formatting technologies into the standard. But yet, to start developing OPC UA applications, you'd need to utilize an OPC UA technology stack that has actual implementation of the technologies required to format and move your data around. So, how do existing technologies get integrated into an OPC UA technology stack? The answer is by mapping those abstract specifications onto a technology of choice using a technological mapping implementation as specified by the OPC Foundation. So, for the entirety of this video, we're going to dive deeper into how that works. Now, for OPC UA applications to actually exchange data, there are three features that need to be mapped to a specific existing technology. These are data encoding, data security, and data transportation. And to address that, the OPC Foundation has a specification document, which is UA Part 6, that defines OPC UA mappings between abstract specifications and technologies that can be used to implement them. Now, before we dive into the actual technologies used for OPC UA communication implementation, let us look at the kind of technology stack that these create when they are combined together for this purpose. So, right at the bottom is the transportation layer, which is responsible for putting data on the wire. On top of it is the security layer, which secures the data before it is put on the wire. On top of that is the encoding layer, which is responsible for converting OPC UA messages into a series of bytes for transmission. These layers are what an OPC UA technology stack is composed of. And then, right at the top of the OPC UA stack is the application layer. This is where an OPC UA application developer develops their application logic using an OPC UA SDK. The function of the OPC UA SDK here is to hide the implementation details of an underlying OPC UA technology stack, such that an OPC UA application developer only has to worry about the underlying stack to a lesser extent. Yes, to a lesser extent, because there is some information that they would still need to know about the stack they are using to develop OPC UA applications. And here's why. There are multiple technologies that can possibly be used for implementing each layer in an OPC UA stack. So what that means is we end up with different possible combinations of technologies for one full OPC UA stack. These different possible combinations of an OPC UA technology stack are called profiles or stack profiles. Now, here's the thing. OPC UA applications can only communicate with other OPC UA applications if and only if they implement the same OPC UA stack profile. Hence, the need for developers to know about the profile of a stack in order for them to choose it. However, OPC UA applications can and do implement more than one profile. Okay, now let's go ahead and discuss the actual technologies used for mapping OPC UA specifications in implementing the OPC UA stacks that we've just described. So we're going to start with the data encoding layer. As already mentioned in this and previous videos, OPC UA applications communicate by using services to exchange messages. And these messages, which include input and output parameters, are typically in the form of structured data, such as arrays and objects that are made up of data elements like floating point values or Boolean values. Now, in order to move this structured data from client to server in a way that the data types of the elements used to make up that structure are preserved on both applications, serialization must be performed on the data. Serialization being the process of taking that structured data, deconstructing it into its individual elements, and then specifically transforming those elements into a series of bytes that can be sent serially over the network. This specific manner of converting an OPC UA service request or response into a stream of bytes for transmission is what is referred to as data encoding. And at the present moment, the OPC UA standard specifies 3 technologies that could be used for encoding OPC UA messages. These are OPC UA Binary, OPC UA XML, and OPC UA JSON. Now, these 3 technologies all need to provide an encoded equivalent for a standard set of primitive built-in data types as specified by OPC UA. In fact, OPC UA specifies 25 built-in primitive data types for which all encoding technologies need to provide an encoded equivalent. For example, how is a Boolean value represented on the wire using OPC UA Binary? How is it represented using OPC UA XML? Or how is it represented using OPC UA JSON Encoding? Now, let us go ahead and describe each of these OPC UA data encoding technologies in detail. Starting with UA Binary Encoding. As you might be aware, most industrial applications are, by nature, time critical. So, for more efficiency and minimized bandwidth usage, the OPC Foundation defined a data format that would provide fast encoding and decoding of OPC UA messages by producing the smallest possible highly optimized data packets for transmission over the network. That format is called OPC UA Binary, and it is the most efficient way of exchanging data between different OPC UA applications. So, to encode in OPC UA Binary format, all the primitive data elements that make up a structure are sequentially written to a binary stream using clearly defined rules. For example, in OPC UA Binary Encoding, the rule states that a Boolean value shall be encoded as a single byte where a value of 0 is false and any non-zero value is true. Now, here's the thing. OPC UA Binary is the most commonly supported encoding technology. So when faced with the task to choose between, say, XML and binary, you should go with binary, unless if the stack profile of the OPC UA application you need to exchange messages with explicitly requires XML. So moving on to XML encoding. So there are some instances where performance must be traded for interoperability. And it is in situations like that where OPC UA XML encoding can be chosen over binary encoding. Reason being that XML is a format that can be easily consumed by many applications at both operations and enterprise levels. And more importantly, it can be understood even by humans. Now, using OPC UA XML encoding, OPC UA data structures are mapped to the structure representation used by XML, and most of the primitive built-in types that are used to construct OPC UA data structures are encoded according to the XML schema part 2 as defined by the World Wide Web Consortium. For example, this is how a string is represented using OPC UA XML encoding. Here, an XML schema is used to define a string element, followed by an instantiation of a string encoded in XML. Now, let us move on to encoding using JSON. Now, in order for OPC UA applications to interact with a wide range of web and enterprise applications that use JSON format for data exchange, the OPC Foundation developed the OPC UA JSON encoding format, which defines standard JSON representations for OPC UA's primitive built-in types. For example, an OPC UA Boolean data type is encoded as a JSON true or false. Here is an example of an OPC UA JSON encoded read request. So as you can see here, the JSON object includes a request header and the node ID of the data point to be read under nodes to read, all made up of primitive data types. Okay, so we've discussed all three data encoding technologies for which OPC UA specifies a technology mapping mechanism. But how would you identify what encoding mechanism an OPC UA server uses? The answer is you will be able to identify and distinguish an OPC UA server's data encoding technology using the server endpoint URL. Binary encoding uses OPC.TCP and then server address, while the XML encoding uses HTTP and the server address. However, it is important to note that encoding is not directly dependent on the protocol. While OPC.TCP is usually used with binary encoding and HTTP with XML encoding, it does not have to be the case. But here's the kicker. An OPC UA server can actually implement more than one encoding technology and use them interchangeably. Bottom line is, OPC UA Binary is the most commonly supported encoding technology, and you are likely to find it in almost all OPC UA server implementations, but make sure to look at the server stack profile, as the transport, encoding, and security policy all have to match between client and server before they can effectively communicate. Now, moving on to the next technology mapping specified by OPC UA, which is data security. So, to map the abstract OPC UA service requests to an existing security technology, the OPC Foundation initially specified two security protocols: WS-SecureConversation, created by IBM, and UA-SecureConversation, defined by the OPC Foundation. However, WS-SecureConversation has since been deprecated due to lack of industry adoption, leaving only the UA-SecureConversation Protocol. Now, before we discuss how UA-SecureConversation Protocol performs the actual encryption and packaging of messages under the hood, let us look at how OPC UA security works at a higher level. So, between an OPC UA client and server, information is exchanged at the session layer, but before a session layer can be created, OPC UA applications need to work out how they are going to secure messages as they are moved from one application to the other. And that process of negotiating a secure communication channel is handled by the underlying OPC UA stack, which creates what is called a secure channel layer. But yet, according to OPC UA specification, the secure channel layer is only an abstract definition, which means that an existing technology is needed in order to perform the actual OPC UA message encryption, which is where the UA-SecureConversation Protocol comes in. Its job is to encrypt OPC UA messages and pass them onto the underlying transportation layer. Now, because of this layered architecture, OPC UA message security is decoupled from message transportation. And the advantages of that are, for example, when a new security protocol comes into play and UA-SecureConversation is no longer needed, it can be simply replaced without having to change this transportation mechanism. Also, you get to worry less about the trustworthiness of a transportation infrastructure because security is embedded on the messages themselves. Now, talking about transportation, the thing is, before the OPC UA client and server even get to the point of negotiating a secure communication channel, they need to agree on the data transportation mechanism that they'll use to exchange messages. And as you'll see later in this video, the OPC specification allows for different transportation technologies to be mapped to its transportation layer. What that means is that the client has to find out what transportation mechanism is supported by the server. Where does it get that information? That information is contained in what is called an application URI, which is the server's unique resource identifier, similar to that used in identifying web servers. For example, to reach Google search server, you use HTTPS followed by www.google.com, with HTTPS representing the transportation protocol. Now, here's the kicker. An OPC UA server is capable of implementing more than one transportation protocol, meaning that there could be more than one protocol option to get to an OPC UA server. Those options are what are called OPC UA server endpoints. For example, a server could have a TCP endpoint and an HTTPS endpoint. Now, as you would imagine, these endpoints could have different security mechanisms. So, to inform the client on what security protocols are required for an endpoint, the server includes that information in what is called an endpoint description. Specifically, an endpoint description would include its URL address, its security policy, which is a set of security algorithms that the server expects the client to use when encrypting messages. Examples of OPC UA server security policies are none, meaning that the client can send messages as clear text, RSA, and AES 256 for symmetric encryption. Next, an OPC UA server's endpoint description would also include its security mode, which could be none, sign only, or sign and encrypt. Now, for the sign only and sign and encrypt modes, the OPC UA client and server would have to acknowledge and verify each other in order to create a secure channel. Whereas, if the security mode is set to none, they don't need to verify each other, but a unique identifier would still be used. Next, an endpoint description would also include its security level, which is a number that an OPC UA server assigns to each of its endpoints to indicate to the client which endpoint the server prefers to use, security-wise. An endpoint with the highest number has the highest preference. Okay, now let us understand how a secure channel connection is initiated. Now, there are cases where an OPC UA client would be pre-configured with the endpoint descriptions required to establish a secure connection. In such a case, all the client needs to do is to select which endpoint it needs and then proceed to initiate a secure connection with the server using that endpoint. And then there are cases where a client is not pre-configured with such information and therefore would have no idea what endpoints an OPC UA server offers. In such a case, the client needs to first send a get endpoints request to the server using a default endpoint description, which can be found at a well-known port using the server's hostname. And the get endpoints request is sent without security. The server responds to this get endpoints request with a list of its endpoint descriptions. Now, because OPC UA uses public key infrastructure to negotiate a secured connection, the server also sends an X509 version 3 certificate alongside the endpoint descriptions. The client would then choose the endpoint it needs and then proceed by selecting a security mode, which could be none, sign only, or sign and encrypt. Next, the client needs to check the validity of the certificate provided by the OPC UA server before it can use the public key that is contained in the certificate to encrypt messages that follow. Now, where does the client get the validation of the certificate? It depends on what certificate management infrastructure the OPC UA server obtained its certificate from. Now, the OPC Foundation recommends using a reliable certification authority and using what is called a global discovery server to manage certificates. However, some small industrial facilities may choose to use a self-signed certificate, which is a certificate that is not signed by any certificate authority. The advantages of a self-signed certificate are that it is easy to make using software such as OpenSSL and therefore does not cost any money. The disadvantages of self-signed certificates are that they are risky because they have no validation from a third-party authority. A general rule of thumb is to use self-signed certificates in a test environment. So in the case that the server obtained its certificate from a certificate authority, the client issues a validation request to the issuing certificate authority. And then, on condition that the server certificate is valid, the client then proceeds to the next step and uses the public key for encryption and signing of its next message, which is an open secure channel request. If the client chose none as its preferred security mode, then the rest of the handshaking procedure is not applicable. Now, together with this open secure channel message, the client sends its certificate to the server, and the server also validates the client's certificate from the issuing certificate authority. Once the validity of the client certificate is verified, The server then responds to the client's open secure channel request and includes a security token for the client to use for creating a session. Now, this should mean that a secure communication channel would have been successfully established, and therefore the client can send a create session request and start to openly exchange messages with the server. But that's not the case, and here's why. Inasmuch as the OPC UA applications would be able to exchange encrypted messages at this stage, they still need to identify themselves first through a process called application authentication. And to authenticate each other, the client and server need to exchange X509 certificates again when creating a session at the application layer. Further, when authentication is done, the OPC UA applications need to go through a process of authorization, which is essentially checking that the OPC UA server's application certificate is on the client's trusted list and vice versa. Now, at this stage, the OPC UA applications would have established a secure channel, authenticated each other, and verified authorization. But what about the human being using these applications? OPC UA requires that they be identified as well to find out what access rights and roles have been assigned to them, and also to use their identity for security auditing purposes. And for that, OPC UA uses tokens to exchange user credentials in order to activate an OPC UA session. A token could be of anonymous type, which means user credentials don't need to be provided. A token could be a username and password. It could be an X509 certificate, or it could be a JSON web token. A JSON web token is essentially the same technology used to log into websites using your Google or Facebook account, and it is what the OPC Foundation recommends. And now, a secure session would have been established, and therefore the client and server can start exchanging messages openly. Now, let us go deeper for a brief moment to understand how the UA-SecureConversation Security Protocol performs the encryption of the actual bytes that get placed on the transportation medium for transmission. First of all, how did the UA-SecureConversation Protocol come to be? Couldn't the Foundation use the tried and tested security technologies such as TSL or SSL? The answer is that when the OPC UA specification was being put together, there were existing encryption technologies such as WS Secure Conversation and the transport layer security. And these could have been directly adopted for mapping to OPC UA service requests, but there were some requirements that were unique to OPC UA that these did not fulfill. Hence, the Foundation took features from both technologies and combined them to come up with the UA Secure Conversation Protocol. However, UA Secure Conversation does not directly map the abstract OPC UA service requests. Instead, it allows secure communication by taking an OPC UA binary encoded message as the payload and then adds additional security-related information in front of and behind this payload. And to cater for the variations in buffer size of different transport protocols, it doesn't apply security to the whole OPC UA message. Rather, it breaks the message down to small chunks that can be handled by different transport protocols and then applies security to these message chunks. Okay, that brings us to the end of security mapping. But as you can imagine, OPC UA security is a big topic, and what we've done here is merely provide an overview. Now, let us discuss the third task that requires mapping, which is the data transportation mechanism. Okay, so we know that establishing successful communication between an OPC UA client and server involves the creation of a secure channel layer and session layer. And both these layers depend on an underlying transportation mechanism to move data between the client and server. So for that transportation mechanism, OPC UA defines an abstract transportation protocol called OPC UA Connection Protocol. And the Foundation specified mapping for the OPC UA Connection Protocol using 4 main concrete data transportation technologies, which are OPC UA TCP, SOAP or HTTP, OPC UA HTTPS, and WebSockets. However, SOAP has since been deprecated. So we'll begin by looking at UA TCP protocol. Now with UA TCP, the OPC Foundation took the common TCP protocol and defined a small protocol that runs on top of it. So essentially, UA TCP is a TCP IP implementation of the abstract OPC UA connection protocol. Now, if you're not familiar with TCP IP, it is basically a two-way communication link with one endpoint of that link having a piece of software whose job is to establish a bidirectional communication link between client and server applications. That piece of software is called a socket, and it is bound to a specific port number, allowing the server application to just wait listening to that port number in case a client makes a connection request. Now in UA TCP, a socket is typically bound to port number 4840 or 4843, and therefore for an OPC UA client to reach an OPC UA server's connection endpoint using the UA TCP protocol, it uses a URL scheme that begins with opc.tcp, followed by the server's IP address or hostname, and ends with the port number. In a nutshell, UA TCP has all the attributes of TCP, with the major difference being that the UA TCP message packets are optimized for size, and they are also transported securely. Further, UA TCP makes the network communication more robust by also defining error recovery mechanisms that enable OPC UA sessions to survive network interruptions. Now, the UA TCP protocol is used for transporting OPC UA data that is encoded using UA binary. Moving on, a UA TCP message chunk consists of a message header and a message body, whereby the message header contains information about the type and the length of the message, and the message body either contains a UA binary encoded message that has been secured using UA-SecureConversation Protocol, or it could contain a UA TCP specific connection message. If it contains a UA binary encoded message, that message ends up being forwarded to the secure channel layer, where it is decrypted and pushed up the stack, where it is decoded and presented as information to the application layer. In conclusion, UA TCP protocol offers the best performance with the least amount of overhead, uses minimal resources, and is therefore preferred for devices at control field level in particular. Now let us take a look at OPC UA HTTPS. Now with HTTPS transport protocol, an OPC UA client and server are essentially exchanging OPC UA messages as regular HTTP messages over an SSL connection. The syntax of the HTTP messages is maintained. The only difference is that a TLS connection is created instead of a TCP IP connection. What that means is that an OPC UA Stack Profile that implements HTTPS for data transportation can also be used with HTTP when security is not an issue. However, the HTTPS transport protocol has no access to the encryption mechanisms that go on in the secure channel layer handshaking. Instead, it determines its own cryptography algorithms that are outside of the scope of OPC UA. HTTPS clients are allowed to have certificates, but they are not required by the HTTPS transport. Now, to connect to an OPC UA server's HTTPS endpoint, clients use the URL scheme that begins with opc.https, followed by the server's IP address or hostname, and then a port number at the end. Message encoding formats that are supported with HTTPS are XML, OPC UA Binary, and JSON Encoding. Finally, let us look at WebSockets Transport Protocol. In a nutshell, WebSockets is a bidirectional protocol for communication via a web server, which is commonly used by browser-based applications to allow the web server to asynchronously send information to the client. WebSockets use the same default port as HTTP and HTTPS and initiates communication with an HTTP request. This makes it very useful in environments where firewalls limit traffic to the ports used by HTTP or HTTPS. So, using this transport protocol, OPC UA connection protocol messages are sent over WebSockets. Now that brings us to the end of this video. Thanks for watching.